Made a mistake near the end of lecture 10, part 2, so I cut that part of the video out, and I'm re-recording this part to go through these slides again. I apologize for the mistake, and here we are talking about how to figure out a optimal structure for the Bayesian network if we do not have domain knowledge to draw the network ourselves. It turns out it's too difficult to do that. We are not going to select from all possible structures, so basically all possible graphs, because there are too many of these and it's hard to compare them. It's computationally expensive to compare all of them. So instead, what we will do is we will just select the best tree structure. It turns out there is an efficient algorithm to do that. And what we want to do is basically a tree that maximizes the likelihood of getting the training data, the same as the MLE maximum likelihood algorithm that we have been using so far. So the name of the algorithm is called the Charley algorithm. So the idea is very simple. We are just going to measure how good an edge is between two features by the information gain. So this is the information gain that we talked about when we were talking about the training of decision trees. So it's exactly the same concept here. The formulas are the same. And we just use two random variables, xj and xj prime. They are features, and we use their frequency in the training set as their probabilities. So we can compute an information gain between every pair of features. And we're going to select the edges with the maximum information gain. So that has a name, and it's called the maximum spanning tree given these edges. So basically, at the beginning, we are going to assume there is an edge between all feature pairs, and then we're just going to select a tree structure based on the edge weights, which is represented by the information gain. And we'll use this resulting maximum spanning tree as the structure of the Bayesian network. So if you have taken 577 or another equivalent course, you know how to find minimum spanning tree, and maximum spanning tree is exactly the same thing. And here I will not go through the details again, but I will briefly talk about this algorithm. And this algorithm is called the Prim's algorithm. And instead of reading through this, I will give you an example, and hopefully it's very clear what we are doing. So the basic idea is we're going to just start with any node or any feature here, and then we're just going to greedily add the highest weighted edge. So let's do that with a numerical example. And let's say there are 4 nodes or 4 features, A, B, C, and D. And we start with this fully connected graph structure. And then let me actually first talk about the mistake I made. So in the previous version of the video, I said there is an information gain of A based on B and the information gain of B based on A, and we're going to select the one that's larger. That turns out to be incorrect because A given B and B given A, they are actually always the same. So that's actually an important thing that I forgot. This equality basically says information gain of one variable given another is always equal to the information gain of another given that one. So the order basically doesn't matter. Information gain is kind of symmetric in this sense. So that being said, we do not actually have these two directions. So there is only one edge here. And then I will suppose it's, say, here's 1, here's 2, here's 3, 4, 5, and 6, or some simple number like this, and we can try to construct a spanning tree from there. So again, the important update is that these information gains are symmetric, so we are not picking the best one from the two directions. So let's start with A. If we start with A, then the next step is, again, a greedy step. We're going to just find the best one connecting the ones we have already with another node or another feature that we don't have. And we want to select the largest one. Here is comparing 1 to 3, so 3 is the largest one. So I'm going to add this edge and I'm going to add this new variable. And next thing is repeat the same thing. Find the edge that goes out of the nodes or the features that we already have to some feature that we don't have. So comparing 1, 2, 4, 5, 6. 6 is obviously the largest one, so we're going to add C here. And at the end, we do it again. That basically consists of all the possible edges, and this one is the next one, and we're going to add B here. So then comes the problem. What kind of direction are we going to use? It turns out any direction works. We just need to straighten this out to a tree. So in particular, we can have something like A goes to D and D goes to B and C. Or we can straighten out another way. D goes to A, B, and C. So basically, there are many different ways of figuring out which direction these edges go, but we need to arbitrarily pick one, and then we just treat that as the root, and then we have a network like that. So in the previous version of the video, I also talked about if we start from some other node, we should get the same structure, and let's try it. So suppose we start with this. Then first we want to add the edge corresponding to the largest information gain, so this one obviously, and then add the next largest one. Then you may be tempted to add 4 next, but turns out it's not between a node that we already have and a node that we don't have. So this is not one of the candidates, so we don't care about that. And among the remaining ones, 3 is still the largest. So we are actually going to generate exactly the same structure. So it doesn't matter where you start, you can always get the same structure. So that's the interesting part of Prim's algorithm. So we can initialize any way we want. And again, important thing is that we can straighten it to make it a tree any way we want. So we need to carefully select which one as the root. And once we selected the root, all the edges will go in the same direction.